Okay, for this example, I've chosen another even-numbered problem from the book. This is number 38. We're asked to graph y equals cosecant of x minus 2 sine x over the interval from 0 to pi. Okay. Now, since sine and cosecant are periodic functions, both with a period of 2 pi, this function is 2. But we're only being able to ask to graph just this part of it, which is actually going to be just half of one of the periods. Okay, so this is an example of a function that is periodic. If we were to graph over an interval twice as long, that would be the entire cycle, and then it would just repeat itself. We're just asked to do this much. Okay, so I know I can't find a y-intercept because 0 is not in the domain. Not only is it not included, but it can't be included because cosecant's undefined there. But I can look for any x-intercept. So that would be where cosecant of x minus 2 sine of x is equal to 0. Now I'm just going to rewrite that as 1 over sine of x equals 2 sine x. So I did two things there. I added this over, and I rewrote cosecant as 1 over sine. And I also realized I meant to say at the beginning of this video, if you want to pause the video and try this on your own, and then check your work by coming back in, I think that would be a great idea. Welcome back. Okay, so I'm going to multiply this over, so I get 1 equals 2 sine squared x. So sine squared x is 1/2. So sine of x would be plus or minus the square root of 1/2. Now, I'm going to simplify that because I recognize that value. That's plus or minus 1 over root 2. And if I rationalize, that's plus or minus root 2 over 2. Now, in the interval from 0 to pi, I'm only going to have solutions to sine being positive root 2 because sine is positive in both quadrants 1 and 2. And I can recognize that the acute angle with a sine of root 2 over 2 is pi over 4. That will be my reference angle for the angle, pi over 4, will be the reference angle for this angle in quadrant 2. So here this angle is pi minus pi over 4, or 3 pi over 4. So I'm just going to mark off, there's pi over 4, there's 3 pi over 4. Those tick marks are just pi over 4 apart. So those are my x-intercepts. So now I want to take a look at what happens at 0 and pi. And I want to do that for two reasons. One, anytime I'm given finite endpoints, I want to see what happens at those endpoints if there are included, or as we approach those endpoints if they're not included. Two, cosecant has asymptotes there, so I'm suspicious that this function might have asymptotes. Remember that cosecant is just the reciprocal of sine. So between 0 and pi, it looks something like so. Okay. So I'm going to take the limit as x approaches 0 from the right of cosecant of x minus 2 sine of x. Now I'm coming in from the right because I want to be coming from this interval. So this is going to be going off to infinity. That's going to 0. So the whole thing's going to infinity. So the y-axis is a vertical asymptote for this graph. If I take a look at the limit as x approaches pi, this time from the left, so that we're coming from this interval, we'll have cosecant of x minus 2 sine of x. That's going to infinity. Again, looking at the graph, that's going to 0. So the whole thing's going to infinity. So I also have a vertical asymptote here at pi. All right, no need to check for horizontal asymptotes because we aren't going to infinity and negative infinity on the x-axis. Okay, so let's take a look at our derivative. So y prime is going to be negative cosecant of x cotangent of x minus 2 cosine of x. That is always defined on the interval from 0 to pi, because cosecant and cotangent are both undefined at those values, but defined at everything that isn't a multiple of pi. So I'm just going to rewrite this in terms of sines and cosines. That's negative 1 over sine times cotangent is cosine over sine minus 2 cosine of x. And I want this to equal 0. So I'm just going to add this over. So I get negative cosine of x over sine squared x equals 2 cosine of x. Now that's kind of interesting, because notice the sine squared is always going to be positive. So this side has the opposite sign of cosine. This side has the same sign as cosine. The only way that can be true is if cosine of x is equal to 0. I could have actually over here just factored out a cosine of x if I preferred. That's another way of looking at that. I could say that's cosine of x times negative 1 over sine squared of x minus 2. This piece will never be 0 because both terms here are negative, but cosine of x could equal 0. And that will be true in this interval if x is pi over 2. So that's going to be my critical number. So let's take a look at a number line. Let's see. I can fit that in here. Let's take a look at a number line here. I'm just going to make it clear that we're only looking between 0 and pi. Okay. All right, so I'm marking off pi over 2. Now, since that's a quadrantal angle, that means here we're just looking at angles in quadrant 1. And if I take a look, this was my derivative right here. Okay. Sine and cosine are all positive here. So this term is negative because of the negative sign there. This term is negative. We're definitely negative here. Okay. Now between pi over 2 and pi, we're in quadrant 2. Now in quadrant 2, cosine is negative. So here, this piece is going to become the opposite of a negative number, so this is positive, minus 2 copies of that negative number, so that becomes positive. So this is positive. So we're going to have a min at pi over 2. So let's see if we can't figure out what that min actually is. So we're at pi over 2, and then I want to plug in f of pi over 2. Probably should have called that function f of x. Okay. Okay, so that's cosecant of pi over 2, which is just 1 over sine of pi over 2, minus 2 copies of sine of pi over 2. And sine of pi over 2 is just 1. So this is 1 minus 2. I'm getting a negative 1. So at pi over 2 negative 1, I'm going to have a minimum value. And now let's just check our second derivative. So let's see, f prime of x we had was negative cosecant of x times cotangent of x minus 2 cosine of x. So if I take a look at f double prime of x, okay, I'm going to just view that negative sign as going with the cosecant as I go through the product rule here. So the derivative of negative cosecant would be the opposite of negative, I'll write them both down, cosecant of x, cotangent of x, those negatives will cancel, times cotangent of x, plus a negative cosecant of x times the derivative of cotangent, which is negative, oops, that's cosecant, cosecant squared x, and then minus 2 times a negative, so it becomes plus sine x. So let's see what we've got here. We've got cosecant of x times cotangent squared x plus cosecant cubed x plus 2, sorry, that's cosecant, not cosine, plus 2 sine of x. Okay. So let's see. I think I'm just going to write everything in terms of sines and cosines. So this is 1 over sine x times cosine squared x over sine squared x, plus this is 1 over sine cubed x, plus this is 2 sine x. Okay, so this is, I can write this as 1 fraction over sine cubed x, combining those two pieces, and that's going to be cosine squared x plus 1, and then plus 2 sine x. Okay, I'm going to stop there because I'm at a point where I can see some interesting stuff. This is always defined on the interval from 0 to pi. Okay. And if I take a look, it's never going to be 0 on that interval. Because on this interval, sine is strictly positive, and 1 plus cosine squared will also always be positive. So this is never 0 on that interval. And I'm also able to see that on that entire interval, it's always positive, so we're always going to be concave up. So I now want to connect the dots. I want to go down and then up, and I want to always be concave up. Got to pass through that point, hit the min, hit that point, and then I had those asymptotes as my starting and ending points. So kind of interesting. It looks kind of like one of the bumps on this cosecant graph, but sort of translated down. All right, so there's our trig example.